Last session of the day. How we feeling? All right, all right. You can do better than that. How we feeling? You guys are going to love Chris Bishop. You are a theoretical physicist. So what are you doing closing out, a day of an AI conference?
That's a great question. So, yeah, my origins go back to theoretical physics. My PhD was in a topic called quantum field theory, which is a very mathematical, abstract branch of physics. And actually, I built it was quite a good career in theoretical physics, about 6 or 7 years working on the plasma physics for fusion experiments. And then it was a very interesting story because Geoff Hinton and colleagues published the famous paper on backpropagation and neural networks. And there was something about it, maybe it was, the HAL from 2001, or there was something about it that really sparked my imagination. And, I had to persuade my boss to buy me a computer. Everything I'd done was with the pencil and paper, right? So I had to teach myself to code, and I started to play with these neural nets. And I just became more and more fascinated. And then I did a crazy thing. I walked away from a perfectly good career in theoretical physics and went into the field of what we now call machine learning and AI. This is like 35 years ago. And so I've been in that field ever since. And what's really interesting is just in the last year or so, things have started to come full circle. I've started to bring my experience in machine learning and reconnect it with the world of natural sciences, physics, chemistry, biology.
Okay, so something tells me that's what the fifth paradigm of scientific discovery is going to be. Let's quickly go through the first four because we should definitely establish what the foundation is before we talk about what you're working on today. So, first paradigm, hit me.
Sure. So the first paradigm probably goes back thousands of years, just empirical observation, just observing, you can imagine a cave dweller, 2 rocks, they think the big one's going to hit the ground first, they let go, they hit the ground at the same time. Why wasn't that amazing? That's a regularity in nature. So the first paradigm is just experimental, empirical observation.
Do you think cavemen were like, aha, gravity?
Well, I don't know what they would have named it, but, it's intriguing, isn't it? It's sort of some of these things are counterintuitive, but I think that's the thing. We observe the fact that there is regularity in nature. It's not obvious that it has to be that way, but we see many, many regularities in nature. So that's the first paradigm.
Let's go to the second.
So the second is when science really begins to take off. And it really stems from really the 17th century. Isaac Newton wrote down laws of motion and the law of gravity. And these are very simple mathematical equations, but they describe the world with incredible precision. And so that was really the beginning of that second paradigm. If you think about the 19th century, Maxwell wrote down the equations of electromagnetism. Very simple, what we call differential equations. You could put them on a t-shirt. They describe the world with exquisite precision over many orders of magnitude of length and time. Writing those equations down is an extraordinary achievement, but solving them is a nightmare. You can really only solve them for very toy problems with pencil and paper. So that brings us to the third paradigm, which is really when we get into the 20th century and we have digital computers. And so one of the first applications, and today one of the biggest applications of supercomputers, is actually solving these differential equations, predicting the weather, modeling fusion experiments, doing quantum chemistry, and so on. Running very big numerical simulations to solve these equations for problems of practical interest. So that's the third paradigm.
Wait, hold on. So you said predicting the weather. Can you give some more examples of like what you explain? So what the problems are that we're solving in this third paradigm, and then how the equations do it or the computers do it?
Yeah, so for example, I mentioned Maxwell's equations of electromagnetism. Now let's suppose you want to design an antenna. You've seen an antenna on a spacecraft or something. It's a complicated thing with bits of wire all over the place. You want to optimize that. Now, it's really just a case of solving those Maxwell's equations, but the geometry is very complex. You can't do it with pencil and paper. So you build some system on a computer. It might be a big grid of numbers, and you're iterating through these numbers, following a sort of numerical routine, and adjusting the parameters of the antenna, a bit like this microphone, I guess, is being optimized so that so that it sounds really good. Also, your antenna works really well. So there are many, many examples. In fact, if you look at the big supercomputers today, almost all of that compute is going in solving these kinds of equations.
Okay, and so you mentioned that, and I'm like, all right, that's probably the end of scientific discovery. But you have two more paradigms. What's the
Right.
fourth?
So in a sense, if we had infinitely powerful computers, we'd sort of be done, right? The problem is that although we can solve these equations, they are extremely expensive. I will give you an example. A few years ago, there was a kind of a tour de force to compute the jiggling and wiggling of all the atoms in the protein coat of the HIV virus, the capsid. And this team used a supercomputer that had something like 4,000 GPU-accelerated nodes. It ran for many, many months, and it simulated the equivalent of 1 microsecond just for the protein coat of this virus. What you get when you do that is it's like a computational microscope. You can measure anything you like. You can measure the ion mobilities and all the things you want to know about. But boy, is that expensive. So that's the third paradigm. Now, the fourth paradigm, and this terminology actually comes from Jim Gray, who was a very famous computer scientist, technical fellow at Microsoft, sadly died in a tragic boating accident. But he really talked about this idea of the four paradigms just shortly before he died. And he was very passionate about the fourth paradigm, which again is enabled by digital computers. And it's the era of data-intensive scientific discovery. Now, we just had a fabulous panel on astronomy, and you saw many examples there of data from these large telescope arrays. Vast amounts of data, truly vast amounts of data, far beyond anything that armies of graduate students could ever process. You need supercomputers to analyze those. And of course, machine learning thrives on big data sets. So machine learning is all over this fourth paradigm. And so we see machine learning at scale trained on observational data, empirical data. So that's the fourth paradigm. And it's worth emphasizing that each paradigm doesn't replace the previous one. It complements and augments the previous paradigms. In fact, the first paradigm is still the ultimate arbiter. In science, you can have the smartest theory, the most beautiful piece of code. If the experiment says you're wrong, then you're wrong. So these paradigms coexist. Now, what we've seen, particularly over the last couple of years, is a sense that we're seeing the emergence of a new frontier. And we're calling this the fifth paradigm, really as a way of distinguishing it from what's gone before. So it again involves digital computation, it again involves machine learning, but machine learning used in a very different way. So machine learning not applied to large-scale observational data, but machine learning effectively trained on data generated by solving those fundamental equations on a digital computer. I'll give you a simple scenario. Instead of using empirical data, you first of all run those numerical computations, those third paradigm compute-intensive simulations of the first principles equations, and you generate training data. Now you burn up a lot more compute, training up neural networks on that training data from those simulations. And what you're left with now is a trained neural network, which of course has the property of being very fast. The inference phase in a neural network is typically fast because it's just a function that you evaluate. So now you've got a system which can, let's say, simulate the behavior of matter, but is now many orders of magnitude faster than that third paradigm, very expensive numerical simulation. And so if you can use that many times, you amortize that training cost over many, many new applications. And even in that simple scenario, we're potentially looking at many orders of magnitude speed up in our ability to simulate these fundamental systems. And when you speed things up by a factor of 2, that's nice. A factor of 10, that's wonderful. When you have several orders of magnitude speed up, you can start to contemplate things that would have been completely out of reach without that approach. So that, in essence, that's the fifth paradigm.
So is the difference between the fourth and the fifth a factor of speed, or is it that you get the neural networks to start creating more data than you ever would have had before? So actually putting them to work to help you solve new questions, or maybe both?
Right, so they're actually very complementary. So the fourth paradigm is trained on this very large-scale empirical data, and ultimately, of course, empirical data represents all sort of ground truth. In the fifth paradigm, what we have is this complementary approach of effectively being able to simulate the solution of those fundamental equations, but many orders of magnitude faster. So that speed up is really at the heart of this.
And it strikes me because when you talk about the fourth paradigm, it seems clear that you can all of a sudden start to solve analytics problems and computer vision problems that you might have not been able to before. But now we talk about this fifth problem, and the science really sticks out because that's where understanding the natural world, being able to run experiments on a scale we haven't before, all of a sudden the natural sciences start to come into place. So when you say that we're starting to do things we were never able to do, is that the right direction, or what do you exactly mean by that?
Well, let me come back to that earlier example of taking a supercomputer many months to simulate just 1 microsecond of the protein code of a virus. Imagine we want to really understand what's happening inside the cell, a human cell, all the processes that are involved. Maybe we're interested in much better treatment for diseases, better kinds of drug discovery, and so on. In principle, as the physicist Richard Feynman once pointed out, we know the equations of physics, and chemistry is just complicated physics, and biology is just complicated chemistry. So in principle, you could simulate an entire human cell by solving Schrödinger's equation at the fundamental level. Now, that's wildly impossible. But what you can imagine is a sort of a hierarchy of simulations. The individual subatomic processes, the electrons interacting with each other at the deepest level, all the way up to protein networks interacting with each other at the cellular level, and different hierarchies in between. And now you can think of machine-learned, we call them emulators. They're very fast neural networks that have learned to emulate the behavior of the very expensive first principles simulator. And so you can imagine a hierarchy of emulators with information flowing up and down that hierarchy. It's a hierarchy of length and time, in such a way that you could begin to imagine, maybe we're talking 10 years away, I'm not sure, but you could begin to imagine doing things like whole cell simulation, which would have been utterly inconceivable as a sort of first principles computation.
So now take me into a more practical part of this, right? So in theory, that sounds nice, being able to simulate the behavior of the cell or understand, a cell on a deeper level. If I'm working on medical research or trying to find a cure to a disease, how does that model now help me do my job in a way that I couldn't before?
Yeah, so great question. So if you think about, you mentioned disease, so think about drugs. So just small molecule drug discovery. So you're trying to find a small organic molecule that docks with some protein. You've identified a target protein, and you're trying to switch on or switch off the behavior of that protein to control some disease. So you've got to search the space of molecules to find one that fits. It mustn't be toxic, and it must be soluble in water and metabolized and all the other things. The space of small molecules of relevance to drug discovery is thought to be around 10 to the power 60. That's 1 with 60 zeros. If we think about materials now, materials for sustainability, new batteries, catalysts, direct air capture of CO2 and so on, new materials is, in a way, that field is in its infancy. The space of possible stable materials is thought to be about 10 to the power 180. That's like the square of the number of atoms in the universe. So think of the atoms in the universe. Imagine each atom itself as a universe with that number of atoms. Each of those atoms is a different possible stable material. How on earth can we explore even a fraction of that space? Because surely in that space of materials are all sorts of interesting things that could have profound practical applications. And so that ability to speed up the simulation of that space, to be able to calculate the properties of materials much, much faster, could be very profound and could have very widespread application.
It all sounds nice. It makes some really good, slides, I'm sure, on a marketing presentation. But you're running the natural science team at Microsoft. What is actually happening practically with this technology that you can talk about today?
Yeah, so we are indeed starting a new team. We launched it a few months ago. Effectively, we're taking a bet. It's a bet that this is an exciting new frontier and very interesting things will happen over the next decade. We are taking a relatively, I would say, ambitious approach to this. So there are lots of things that can be done today by way of taking these existing simulations and speeding them up. And we're looking at some of those, how to do a better job of predicting the weather or just simulating fusion reactors is another thing we're looking at.
Does looking at mean doing, or does looking at mean looking at?
It means actually doing. It means solving those equations, working with partners. So you say, why Microsoft? Why should Microsoft be in the space of natural sciences? I think what Microsoft brings is expertise in large-scale compute, expertise in machine learning and AI, and then we work with partners. So our partners in fusion research, partners in, we have a close collaboration with Novartis in drug discovery, where we're actually using these techniques with Novartis to look at that challenge of small molecule drug discovery, accelerating that exploration of space, of the space of possible molecules, and it's highly practical. In fact, Novartis right now are actually synthesizing some molecules that have been designed by our AI and testing them to understand their properties as potential drug targets. So it's very real and very practical here and now. But the reason that we're starting a whole new team and not simply adding this to our portfolio of research is that if we take that longer term horizon, we see this as really quite transformational, perhaps even worthy of that name, fifth paradigm.
I mean, better be worthy. We're doing a talk on it, so.
Well, it better be, yeah.
Yeah. A controversial question, but does this, now, if you're able to simulate cells, behavior, and biology in a way that, might even be better than what we can do looking at the natural world, does this eliminate potentially the need to do gain-of-function research like we see with lots of viruses, which, has received a lot of heat in the wake of the coronavirus?
So I think, these, as I said before, these paradigms exist in this very complementary way. And so it's not that new approaches necessarily eliminate alternative techniques and so on. It's really rather more that it expands the set of tools that we have available. In fact, if you imagine, let's say again, looking ahead a decade and being very speculative, you could imagine a scientist has access to powerful AI tools, which are effectively agents. They're using techniques like reinforcement learning, active learning, and those agents have access to all of these paradigms. They could run, let's say, large-scale experiments automatically in big automated wet labs. They could run first-principle simulations, the very computer-expensive ones that I talked about, but are known to be accurate because you're starting from those first-principles equations, or having access to these very fast neural emulators that can explore the space very quickly. And can draw upon those resources in a way that makes the right decisions, almost helping to automate that scientific loop of formulate a hypothesis, gather some data, use the data to learn more about that space of hypothesis, and guide the next set of experiments that you do. And those experiments can be a mix of, in silico and wet lab experiments.
It's interesting that you're talking about supplement versus replace. I would imagine you'd be standing on the table for replace, not only because it benefits your interests, but also because experimentation can be dangerous, especially when you're talking about making new materials, experimenting with chemicals, and experimenting with biology.
Well, with a lot of these experiments, the big challenge is actually really throughput. It's not so much the danger of the experiments, it's just the sheer scale. Again, you saw that in the astronomical setting, if you think about wet lab setting. It really comes down to the fact that if we think about materials, molecules, drugs, and so on, that space is just combinatorically vast. And so it's really about how to accelerate the search for new materials, new drugs. And so it's about addressing that combinatoric search. So AI machine learning features in many different ways, but including, I think, in the future, increasingly through these very fast emulators.
Okay, I have one more question, and then I'm going to open it up to the audience. So if you have a question, start thinking about it. In the meantime, though, I'm going to ask you this. This research is experimental. You'd agree, right?
All research is experimental. If you know the answer, it isn't research, yeah.
Great point. But it's not generating immediate profits, or is it? I'm asking because right now we're going through a pretty serious economic downturn. I haven't checked Microsoft stock today, but I imagine it's down anywhere between 17 and 25% on the year. And tech giants are pulling back on more experimental projects that aren't generating profits right away. So do you believe that through this current economic downturn, this is going to be something that Microsoft will continue to support? And if so, why?
Well, obviously we have to think about the near term in terms of economics, but also we have to invest for the longer term. So one of the big motivators for Microsoft in this space is that it really does address some of the most profound challenges that humanity faces. So climate change is a great example. These kinds of techniques are directly relevant to technologies such as direct air capture of CO2. And that's something we have to invest in now, right? If computation really can make a dent in that problem over the coming decade, it's not enough waiting for a good economic cycle. We have to be investing now. And so that's why we're very actively building up this team of scientists right now, because we want to be on the front edge of what we see as an exciting transformation. And I've no doubt there will be near-term benefits, but we want to take a long-term view as well.
And the benefit is that if you do invest through whatever economic downturn that we have, you end up probably ahead of the competition, although some people who are not working in big tech might be like, let's give us a chance. But if it starts to do some of this work that you're talking about, help us cure disease, help us make new materials, think about our planet in a different way, that sounds pretty good. Okay, why don't we turn the lights on and open up to questions? As we go to, we already have a bunch of hands up. So as we go to questions, I would like to make a request, no speeches, please, and keep it on topic. And do we have mics? Because I can't see out there. But if we do, then someone should ask a question. Go ahead. If you have a mic in your hand, go ahead. And introduce yourself.
Hi. Hi, my name is Fromsa. I'm a consultant.
Speak up a little bit.
I'm a consultant
Great.
working at Itera from Norway. And I appreciate your fifth paradigm view. And I'm going to challenge you a bit more and ask you, what is the sixth, if you could imagine?
What's the sixth paradigm?
What's the
Chris?
sixth paradigm?
Great question.
Is a great question. I have absolutely no idea what the sixth paradigm is. We're like super focused on the fifth. My guess, and it's the bet that we're taking, and we're making a very big bet on this, is that science and technology doesn't sort of progress uniformly on all fronts. I mentioned, the 17th century, the 19th century, electromagnetism, the beginning of the 20th century, this huge wave of advancing quantum physics. As a research scientist or as somebody investing in research, it's key to think about, where's that next wave of advance coming from? And so really the gamble we're taking, it's not that this will be interesting, right? This will be a very interesting domain. Lots of useful things will come of it, I'm sure. The bet that we're making, and there's no guarantee of this, the bet we're making is that over the coming decade, this, what we're calling the fifth paradigm is just a convenient way to talk about it, but this frontier will be transformational, that it will advance very rapidly. So I think it's a very safe bet, because I think we can't go wrong, but we're hoping that it'll be something very big.
Maybe the sixth paradigm is conscious AI? Oh, okay, I'm kidding. We bring it back to the first panel. Okay. Let's see. Who else do we have? Maybe someone in the middle here. Go ahead. We'll just take whoever's closest to you. Yeah.
First, thank you very much for this interview. It was quite informative.
All right. Speak up a bit.
Okay. Is this better? Okay. So I'm a graduate student at the University of Amsterdam. I study AI. And so I have read your words. It's nice to listen to them. So one, I guess it might be it's a problem that you might be facing or some sort of technical issue. But okay, so the third paradigm includes stuff like researching, all the basis functions all the base functions in physics, etc. But that comes with a level of uncertainty and some sort of stochasticity in some cases, or some chaotic in terms of the deterministic case. So neural networks are quite deterministic in that sense, and they come with their own levels of uncertainty. So how do you know what you're simulating, or at least at the top of the hierarchy, is actually what is real? Or how do you quantify that uncertainty, for example?
Yeah, it's a great question. I mean, the equations themselves are deterministic. Schrödinger's equation is a deterministic equation. The interpretation of the wave function is a probabilistic interpretation. Navier-Stokes equations are deterministic, but they can be exponentially sensitive to initial conditions and the butterfly effect and so on. And so neural networks can capture that very nicely. So it's a very natural paradigm to use. The point about uncertainty is a super important one. In fact, one of the things we'd love to be able to do with these emulators, so I talked about huge acceleration. It sort of comes for free. You can't help but go much faster because you're replacing this very, very detailed iterative numerical computation with huge grids and so on with basically just a function evaluation. So it's just orders of magnitude faster. The secret is not just to get the answer, thousands of times faster, but to get the right answer, right? And so neural networks you can think of them as sort of function approximators. And so when they're working, broadly speaking, within the domain that they've been trained on, they can produce good answers. If you extrapolate to new domains, they may produce bad answers. That's okay if you have a really good quantification of uncertainty. And this comes back to, I was speculating about that idea of agents, 10 years from now, running these kinds of experiments. If you can quantify the uncertainty in your emulator, your agent can be exploring the space of, let's say, new catalysts, for example, and it can start to find something interesting, but it wanders off into a new regime. Now, if your neural network comes back and says, well, I'm not sure what's going on here, this is my best guess, but I'm now getting very uncertain, that agent could say, no problem, I'll go back to the simulator, the expensive simulator, run it again, and get you some more training data, especially for this new region, and you can bring down your uncertainty. So the quantification of the uncertainty actually becomes a first-class citizen of the whole paradigm and becomes extremely important. So yes, uncertainty will play a key role in this. Yep.
Hey, Chris, student from University of Amsterdam.
Hey, well, fantastic. Well, it's funny you should mention that. So of course, obviously we're in Amsterdam today, and we're growing this new global team, and we announced fairly recently that we're opening and have opened a new research lab dedicated to AI for science, and it happens to be in Amsterdam. Hear it for Amsterdam, come on.
Well,
So
thanks
very exciting.
everyone, and thank you, Chris. This has been a blast.
No, thank you, Alex.
Here we go toward the fifth paradigm. Thank
Great,
you, everyone.
Thank you.